Hi there, and thanks for joining us for this webinar on strategy for using science Inc. phenomena effectively. My name's Francis Vigin. I'm CEO and founder of KnowAtom. I'm a former teacher. Founded KnowAtom about 13 years ago now, and our organization is located just north of Boston in Salem, Massachusetts, and we're a team of educators who have developed a K-8 solution for science, technology, engineering, and math instruction, but the context of this webinar is one that has been a big part of our evolution over the last 13 years, which is the next generation science standards, and how to effectively engage students and use what's now being referred to as anchor phenomena or phenomenon to drive instruction, and how to have phenomena be really the fabric of everyday teaching and learning. So with that said, the reason that we're so engaged by science and engineering here ourselves professionally is that we see it as the perfect opportunity to teach critical thinking skills that scientists and engineers are, and specifically by putting students in the role of scientist and engineer, that scientists and engineers are using those critical thinking skills, the creative, evaluative, and analytical thinking skills that we want as part of every part of our curriculum to actually develop and use their knowledge. And so that's something that really resonates with us in particular with the switch to next generation inquiry instruction. So with that said, I would like to give you a quick heads up. If you are in the live session, if you have questions, please feel free to drop those questions into the little question panel on your screen. And I will do my best to address as many of those throughout the presentation. If you'd like something clarified and so on, I will do my best to try and take questions, do a little question and answer time at the end. However, I have a pretty hard stop today, so we're only going to be able to go about an hour. So I'll try to pack as much in as I can in the first 45 minutes. The agenda for today is taking a look at basically these 5 core areas that relate to both strategy and effectiveness of using science phenomena. First and foremost, what are phenomena? How do we qualify a phenomena-centered classroom and curriculum? How to choose phenomena appropriately? Implementing that phenomena within actual lesson and unit flow. So, we have this idea of a phenomena, well, where does that belong? And how is it a little bit different as you kind of look at the tiers of early elementary, middle school, and if there's any high school folks, we can talk about high school as well. The connection between phenomena and standardized testing, and this is a key one. If you're from DC or Illinois, you've already seen this in play. You may not have recognized it as phenomena, but we're going to talk a bit about that. So let's jump right in here. So what are phenomena? Well, a phenomena is the context that motivates the work of a scientist or engineer. In plain language, a scientist or an engineer doesn't go to work to remember things. That's not why people hire them. Scientists and engineers function in a context to actually develop and use that context. And specifically, when we talk about scientists, what they're doing is they are focused on answering questions about observable events. Okay, and they're answering those questions by developing and using their knowledge to test hypothetical answers to those questions. So for a scientist, a phenomena is an observable event. So if you think of the examples in a K-12 context, an observable event could be an autumn day. It could be the slip and fall phenomenon that we may see on a winter's day. It could be organisms eating. It could be seasonal light patterns. It could be computers crashing. These are all observable events. Okay, a context which a scientist could then develop and explore, all right? It could develop a question around and attempt to answer by testing a hypothesis. For an engineer, their context, what their role is, have to do with a problem that may be solved by extending their knowledge of science. So a way to think of this is street flooding, fuel consumption, how to observe objects that are far away, traffic, how to get from one point to another quicker, how to make boats travel faster. So an engineer, their context has to do with a problem. Scientists are more dealing with an observable natural event and trying to explain it. Okay, so scientists think of it that way. Scientists are trying to explain observation, what they're observing, by testing hypotheses. Engineers are trying to solve problems by using their knowledge and prototyping. Okay, so the reason that this is important is we have to understand that scientists and engineers have different motivations. The context that motivates them, the context that they work within, are nuanced and different. And they connect to what's called the nature of science and engineering. And so the nature of science and engineering is interconnected. You'll notice that in this previous slide, engineers need to use their knowledge of science in order to solve a problem, like street flooding, for instance. Well, the way it works is that scientists are asking questions in the context that they're working in and developing new knowledge as they experiment and come to evidence-based conclusions. That knowledge is used by engineers to solve problems that they're identifying. And they're doing that by prototyping potential solutions, testing them, and coming to evidence-based conclusions. What engineers develop is considered technology. Technology is anything that solves a problem. So it's not just electronic. Door stops, latches, hinges, doorknobs. I mean, simple machines are all examples of technology. And the reason that you see math in the center of it here is just as a tool for communication. Math helps us quantify, analyze, evaluate, and communicate our observations and also our opinion as well, and sort of reflect back on our prototype or on our hypothesis with evidence, with concrete evidence that's verifiable and replicable. Okay. That said, a lot of folks, when they hear a phenomenon, they think, okay, questions and problems, think about the context that a scientist or engineer is working in, prototyping and experimenting. They will often think of problem-based learning and hands-on inquiry. The issue, and this is kind of a common issue in education, is that people people, the masses, there becomes a mainstream kind of fractured concept of something like hands-on learning or inquiry or problem-based learning. And so new terms get invented to try and say, no, this is what we really mean. It's not exactly like that. So problem-based learning, so using problems, engaging students in problems to drive instruction, absolutely can be next generation. Hands-on inquiry absolutely can be next generation. However, the reality of the way that problem-based learning and hands-on inquiry is implemented in the classroom oftentimes misses the mark. And we can talk more about this if anyone has specific questions, but in order for problem-based learning or hands-on inquiry to be effective and aligned to NGSS and implementing phenomena appropriately, it's important that it's authentic and student-centered engagement. The whole idea of using phenomena as part of the next generation inquiry environment is it's a context to engage students as scientists and engineers, and we'll get more into that in a second. But that means that it's authentic and student-centered engagement. It's not something that you hand students to fill out. It's not a procedure that students are given. It's not a make-by-number. It's not a workbook with like a series of questions and something you display on the board. It has to be the ideas coming from the student. Secondly, it has to require critical thinking skills, creating, evaluating, and analyzing those higher order thinking skills. just because students have hands-on materials, they could be playing. If the and it's a fine line where sometimes entertainment value can trump actual learning, and so while the two are not mutually exclusive, it's really important that creative evaluation and analytical thinking is a part of problem-based and hands-on inquiry, and that there's not some tool that's trying to scaffold around that. Students also must be engaged in developing their own knowledge with their own skills. So this is the kind of bootstrap context for phenomena. So a problem-based learning environment, often the problem is kind of building out, or it's the kind of engineering side of phenomena that we just talked about. Hands-on inquiry, there's a much broader spectrum. It can be anything from sort of playing with materials and loose discovery to something that's much more structured that requires students to methodically engage in science and engineering practices in order to develop and use disciplinary core ideas and cross-cutting concepts. So that's what I mean by number 3 here. Number 4 is that students and teachers too need to be able to monitor and learn students learning specifically across all 3 NGSS dimensions simultaneously. It's not the kind of thing where we learn, and this is key piece of phenomena. It's not that we learn facts and then we learn the systems dynamic and then we learn skills independently. It actually requires all 3 at the same time. Okay, because again, when we think about the context in which a scientist or engineer is functioning, what they're doing is they are using their skills as scientists or their skills as engineers to pursue a question towards an evidence-based solution or evidence-based answer, which is that knowledge, or in the case of engineering, to pursue a problem towards an evidence-based solution. Okay. Now, there is a big shift going on here, and so using phenomena in the classroom, before we get to kind of how to qualify this phenomena-centered classroom in a curriculum, I want to point out that there is basically a traditional model of instruction, which is true K through 12, that you'll find out there. And then there's the next generation model of instruction, which is far less common, but is something that you can find out there. So a traditional model is one that phenomena is kind of an add-on. Okay, it's sort of it's used as a hook. It's a almost a trick to try and engage students, or a quote fun, flashy kind of a thing to do. In a traditional model of instruction, content flows through the teacher, and the teacher is playing this sage, this content expert, who demonstrates the phenomenon, who models the facts and explains what that is all about. In that traditional environment, students are filling out sheets, they're reading a text, they're recalling facts, they're repeating demonstrations for themselves, they are summarizing the phenomenon that was explained to them. And so really, this is a repeat recall model. And it's very popular in traditional classrooms because for a teacher, if I give you X and you give me back X, then I know you're proficient. And that was kind of acceptable. It's not really ever acceptable, to be honest, but it was something that under previous versions of the standards, which were very fact-focused, is something that people could get away with and not really know the difference between the traditional model and the next generation model. So a next generation model is one where the teacher plays the role of a skillful coach who helps strengthen the connection between students and content by helping the student develop those science and engineering skills, the practices, and use those skills to develop and use the disciplinary core ideas, which is the content, and those cross-cutting concepts, which is the systems dynamic, and how content is related through systems. Now, this is much more dynamic. It's much more skillful. It's helping students learn how to navigate the gray areas. And what happens is, as students are developing skills, teachers are changing those supports, and they are increasing rigor, or essentially maintaining rigor. But what's required to maintain rigor is actually increasing oftentimes expectations, removing supports, redirecting and monitoring, putting thought partner, a role in accountability. So it changes what it means to be proficient. In this situation, a student who's proficient has to be able to demonstrate, and so we think about the new standards as performance expectations. A student needs to be able to perform the expectations of the standard by developing and using the content, to be able to solve problems and answer questions as a scientist or engineer would, and to be able to make connections across the content by describing its interaction. So the focus of the new standards is, yes, it's three-dimensional. So you have a performance expectation. Well, it doesn't exist in isolation. It actually has a skills dimension, a content dimension, and a systems dimension. But it doesn't exist in isolation from other performance expectations either. So what I'm showing you here is just one. But actually, the context in which students would engage as a scientist or an engineer would actually combine multiple performance expectations and different elements of the foundation boxes that you see here. The reason that this phenomena is so important, and why this next generation model of instruction is so important, is that in order to perform the expectation, students need to be engaged in higher order thinking. The focus here is in real world context. Okay, that's what phenomena is. A phenomena is being able to observe physics. We could use this as an example. You know, when two objects collide, there are natural laws which carry out or govern what happens when those two objects collide. So when you think about that context, when you see objects collide, we can actually explore that phenomenon, not necessarily by remembering, understanding, and applying the facts related to it, but the next generation science standards really want us to evaluate it, analyze it, and create something out of what we're seeing that deepens our understanding of that collision, of some dimensions of that, perhaps the effect that mass has on how one object moves relative to the other, or how high a ball bounces relative to where it was let go from, or its mass, things like this. So the demands on higher order thinking only come to light if the classroom environment creates the space for that, the opportunity for that for students, and if teachers are not playing sort of the conduit role, getting between the content and the student, but instead playing the coach role, okay, and creating an environment that requires students to develop and use that context. So how to qualify a quality phenomena-centered classroom and curriculum starts with really asking yourself, are students engaged as scientists and engineers? Key to that is shifting the student from doing science to actually being scientists. It's one of the kind of hidden truths of what oftentimes traditional classrooms will say, is that, well, we're doing science, and that's probably true, doing it by rote. But in fact, students need to be engaged as scientists or as engineers. And that shift can also be thought about as a shift from learning about something to actually figuring out aspects of a context. And that context, again, is a phenomenon. So figuring out aspects of what happens when objects collide, in my previous example. Third is thinking about, are students empowered to build a framework of understanding that actually is the world around them? One of the things, so real world versus not real world. Real world is, literally the world around us. What is not real world? Things like shaving cream clouds are not real world. Skittles, representations of different things are not real world. The cell cake is not real world. All these things that are often, part of traditional curriculum, and you can find them out there, just Google, go on Pinterest. A quality phenomena-centered classroom is empowering students to build a framework of understanding out of something that is actually happening or has actually happened. And we'll take a look at that a little closer. So, we could look at Superstorm Sandy as an example. Okay, that's a real historical event that we can actually, it's very complex, that students can begin to unpack and build a framework of understanding around that. Thinking about, that knowledge built in context, kind of building on number 3 here, that knowledge built in context makes the world itself an anchor to transfer and deepen understanding. So what I mean by that is, if a student learns, and if what drives instruction is real world context, quote unquote phenomena, then what students are learning to do is to analyze, evaluate, and create in the context of the real world. And by virtue of doing that, the real world around the student is actually the anchor for their understanding. And I don't know if that's too nuanced, so if anybody has questions about that, please ask. But it's hard to remember facts that have no context. But it's when you understand context, it's easy to see that context everywhere. And to then have that context be essentially your filing system for the knowledge and the skills that you've developed, and to then be generalizing and applying that more broadly and in deeper context. The 5th piece of how to qualify quality phenomena-centered classroom experiences and curriculum is really seeing students as identifying STEM, science, technology, engineering, and math, because these pieces all come together. And I know the arts and language, and we can keep building out the acronym. But this is an opportunity that students should be identifying this as an environment or opportunity to understand and shape their world. So there's a big piece of empowerment that is a part of both the classroom and the curriculum. And the thing is that the curriculum and lesson plan design gives or produces the inquiry environment experience. And I never really broke this up before and emphasized this until I was in a meeting recently where some middle school educators said, well, aren't these different things? And they aren't. The curriculum and lesson planning is not different from the next generation inquiry environment. One produces the other. They are linked, inseparably linked. And so you can think about it as, if you look at somebody's lesson plan, would you want to be part of that class? Is that a class that you would like to be, sitting in on every day as a student, learning in? Or would you rather be in a different type of lesson? Okay, because you can anticipate the experience. Okay, that's just kind of a little self-reflective exercise there. I'm bringing up that same performance expectation again, just to point out that these 5 things that we just talked about are that curriculum and that classroom are what brings these 3 foundation boxes to life and gives students the opportunity to try to develop a model to describe the movement of matter among plants, animals, decomposers in the environment, or essentially to try performing the expectations of the standard. Okay, that's why it's called a performance expectation. Now, getting further into the phenomena itself, there's 2 flavors of phenomena. Kind of one hangs on the other. There's this anchor phenomena, And then there's the investigative phenomena. So the anchor phenomena is that observable real-life context that's broader, and it's the basis to be questioned, or the problem, the basis of the problem to be solved. And it's very complex. Okay, it's something that we can't sort of just solve or answer with a single experiment or a single prototype. Okay, and an example of that might be flooding in New York City. Okay, there are many reasons that New York City could experience flooding. But that gives us a frame to the lesson. Okay, we'll go into that a little bit more in a second. The investigative phenomena is what is observed as a result of testing answers to questions about the anchor phenomena, or what is observed as a result of prototyping solutions to the problem identified in that anchor phenomena. So the investigative is an offshoot of the anchor. Okay. So an example of this would be, okay, so if you think about the anchor phenomena being the flooding in New York City, an example of investigative phenomena related to that would be how soil and ground cover affects water seepage, right? Because that is an element of that affects flooding, okay? And it may be a part of answering the question of why flooding is occurring, or solving the problem of alleviating the flooding, okay? So how to choose anchor phenomena? Some people might think of it as design. You can't really design a phenomenon, right, because it's natural. But you can choose it, and you can sort of augment that context in such a way that it's more relatable, more age appropriate. But how you choose the phenomenon, thinking about anchor first, right? You want to think about a context that gives the lesson overarching focus, okay? And I say lesson here because some people might think of it as unit. The old 3-unit-a-year model should disappear if it hasn't already disappeared from your class. You know, the idea that classrooms can spend months with some kind of anchor as whales, you know, that's boring. It loses. That's how you get oftentimes scope creep, and things get off track in terms of not necessarily being relevant to the standards. So having units that are like month-long units, that's what we do. So we have 9 units in a year, unless it's kindergarten. That's a little different. So that you have sort of an overarching focus to the unit. But the anchor phenomena really gives focus to the lesson. Okay, so for instance, in the case of the flooding, we may have a story about flooding in New York City. The second piece that falls out of that anchor phenomenon, so the story about flooding, is students questioning and connecting with that phenomenon to drive teaching and learning. Okay, and an example of this is concept to concept, concept to self, concept to world connections. So you could picture a story about flooding in New York City, nonfiction, right? And then having a Socratic dialogue where these concept to concept, concept to self, concept to world connections are occurring. And the role of the teacher in this anchor phenomenon is to act as Socratic coach, thought partner, accountability partner. Okay. Now, transitioning from that anchor phenomenon, okay, so we've made some connections, we've had a discussion, we've encountered a complex situation, this flooding. What do we do now? Well, we get into that investigative phenomenon. So the learning environment has to create an opportunity to develop and use elements of that story to actually investigate them. That's what it means to investigate, to develop and use the elements. Okay, and those elements are coming from the anchor phenomenon. So it's an investigation of some aspect of the anchor phenomenon. And here, an example is giving students the freedom to investigate things like soil permeability. Okay, and I use the word freedom. It's tough. It's tough to find a word here that fits well because, an investigation is not telling students what to do. That's not a student-centered investigation. A student-centered investigation is really giving students the freedom or the liberty to choose an aspect, or at least have their own ideas within some boundaries, so that there's variation between one student's approach and ideas and thinking and another's, or one team's and another. So it's not about a single linear path, but in fact, it's much more like the channel in a harbor. The boats have to stay sort of between some structure, but there's a lot of breadth of where they can be, okay, to the left or to the right. And so that's an element of freedom, and that's something that a lot of folks, unfortunately, don't give students, because they don't give a full release of responsibility to students. And there is not a process framework in place for science or for engineering, so that students can apply their science and engineering practices to logically pursue a question or a problem towards an evidence-based solution or answer methodically. Okay, so students aren't really equipped for that. So, teachers react by pulling that control back into their own sort of self and reverting to a traditional model of instruction. The second piece of investigative phenomena is, and think about investigative phenomena as being what students observe, okay, as a result of their investigation. So students, in order to observe something in their investigation, need to be able to investigate. That was number one, given that opportunity, their own idea. They need to be able to apply that science and engineering practices in the logical framework we just talked about. So the example of that is students have an idea about soil permeability. Now they need to plan an investigation. Okay, now they execute their plan. Why do they do that? They collect and reflect on their results. Okay, and then as a class, you come back together, think about different approaches, different findings. This is where the scientific argumentation and arguing from evidence comes in. Okay, and that's where number three, the direct connection between the student's investigation and that knowledge and skills to understand the anchor context happens. So what happens is that anchor phenomenon is better understood as a result of the investigative phenomenon. So the investigation is digging into some aspect of the anchor, gathering data, forming a conclusion, and then reflecting back not only on the investigation, but on the larger anchor, the larger context as a result of that. And that's how lessons scaffold within a unit, because you can bring different anchor phenomena to light. And the thing is like, there are gray areas here, because a unit itself has a large context, and then each lesson kind of has a smaller context, and each investigation has a context that's unique to the student team. So I don't want to dizzy people too much, but I'm trying to be as specific as possible, but general enough that you could apply this in your own context. Or if you'd like, you can take a look at resources that we've developed, which use all of this and have built this out entirely, and see how that plays. But the third piece, so to give you a for example of what it means to connect, have a direct connection between the student's investigation and the anchor context. So we were talking about soil permeability, right? Because that has to do with water going through the soil. Would be helpful to know about this if you are digging into why New York City was flooding. And so an example would take away for students would be native clay materials have porosity characteristics similar to concrete when faced with large volumes of water. Why would that be important to reflecting on the larger context? Well, one of the potential solutions may be to remove things like concrete to expose the natural materials that are there. If the natural materials are clay, then that may not be the solution. From a scientific standpoint, somebody may have the hypothesis that it's the clay, or that it is the concrete that is causing the water that's entering New York City to not be able to percolate through the the ground and dissipate. And so this knowledge that the native clay materials have porosity similar to concrete when faced with large volumes of water actually develop and use that context and help us get closer to understanding it or closer to solving the problem. Okay. Now, the way that works in the classroom is so how to implement that within a lesson flow, K to 8. This is one example of a lesson. Okay. Now, when we talk about a lesson is a group of experiences, and they are deliberate practice. They are deliberate, thoughtful experiences that come together in the following way. So think about a lesson is taking place, we'll use a middle school example for right now, over the course of 5 days. Okay, because let's say you meet with your students every day for 45 minutes, 55 minutes, or something like that. What you may have is a kind of read aloud visual, some kind of media that brings that anchor phenomena to life. Okay, so students encounter the anchor phenomena. The flooding in New York City, for instance, the article about that. Then the next day, or as part of the second half of that class, you engage in Socratic dialogue to unpack students' observations about that anchor phenomenon and to ask them questions that require them to create, evaluate, and analyze and actually form those connections that we were talking about earlier, the concept to concept, concept to self, concept to world connections. We're still at the anchor phenomena, though. We need to transition into that investigative phenomena, really by releasing the responsibility to students to outline their individual or their team's investigative approach. Now that we understand the anchor phenomena a bit, or we've talked about it, we've connected with it, what am I as a student or as a student team, what are we going to investigate? What are we going to dig into about this anchor phenomena? And how are we going to approach that? Okay, so, so we are either going to be in the role of scientist or engineer. So we outline that investigative approach, and then we actually get into the investigative phenomena by carrying out the science or carrying out the engineering that we've outlined. That's why planning is so important. And so this is where we encounter other phenomena. Okay, and I don't mean to keep using this word phenomena. What is phenomena? It's something that you can observe, right? It's something in nature. So the anchor phenomenon is that large context of the flooding and kind of the drama and what happens there, some of the different elements. In terms of the investigative phenomenon, as students are carrying out their experiments or their prototyping as scientists or engineers, they are going to be observing nature again, but they're going to be observing isolated elements. So earlier I mentioned about clay versus concrete. Students would be observing how the water travels through clay, how it travels through concrete, the time that it takes, the volume that's produced in that time, that's able to make its way from the top to the bottom of that surface. Okay, so that's where they encounter investigative phenomena. And the fifth part is where students use those observations to unpack the investigative sort of approach, the observations, and relate it back to not only their hypothesis or their solution, which was the center of their plan, but the larger anchor phenomenon context. Okay, so you can see that you start with an anchor phenomenon, and then you kind of go through this, and this is the fabric and the fuel of the investigation. Okay, this is how teaching and learning happens in a next generation inquiry environment. And of course, you would get to the end of this, and we would then transition to our next lesson or unit. So, maybe we're talking about flooding in New York City, next time and soil porosity and all this sort of thing. The next time we may talk about something like runoff and pollution and public waterways. And so we can bridge from one to the next, okay? Um, at an early elementary level, what changes is the complexity and the modality. So, at an early elementary, read aloud instead of students having individual, reading um, material because, well, they can't read yet. Um, as they plan investigations, the way students plan may be more visual and verbal than, what a fourth grader would be doing in a blank composition notebook, or a fifth grader. And you may say, oh my goodness, our fourth or fifth graders don't do this. Well, ours do, and they're capable of doing that. But that's, again, a function of expectations, and so on. So, I won't belabor this too much more, but this is really core and key to having an anchor phenomenon drive teaching and learning in the classroom. Bringing up that same standard I had before, this is how, if you're familiar, and I'm assuming if you're in on this webinar that you're at a deeper level with these next generation science standards than some folks, that's how these performance expectations come to life in a lesson over the course of a few days, and how we can continually challenge students in a way that exceeds their skill set over time. We can bring the standards together in real life and nuanced ways and integrate, okay, and achieve the goals of the evidence statements. Get students to a point where they have developed these habits to be able to be observed producing evidence of learning in a novel context. Because that's what that's what any phenomena is. It's a novel context. That's why the phenomena comes first. That's why in a next generation environment, it's a you do, we think, and almost never do I do type model. Completely the opposite of what many people are used to, especially in ELA, where people are always talking about I do, we do, you do. It doesn't work that way in science and engineering. It doesn't work that way with the new standards, because students can be developing and using their knowledge and discovering why things are important even before even before they realize something's important. They've already encountered it, they see it, they start to build that framework, they link it to a context and observation, and then later on it becomes more and more valuable as they try to use what they've observed in investigation to explain their ideas, their approach in that outcome, but also how it relates to that larger context, okay? So I'm just going to blast the last couple slides and try and take some questions here. I know we've got a few lined up. So that's why grade, you can't have, you can go to NSTA and it's like, I lose my mind. The NSTA bookstore is like, I wish they had, you could go around stickers and say, what not to do, because the NSTA bookstore is full of things you should not do. You cannot have just units and lessons that are, could be third grade, could be fifth grade, could be eighth grade, whatever. It needs to be grade specific. You need to have very thoughtful progressions and scaffolding in order to make the most out of that student time on learning and to be able to intentionally nurture student skills and knowledge. Because that's what we're talking about here. And what I'm showing you is a scaffold summary of our different units. And you can see how these are very intentional. Look at grade 2, learning about Earth's surface, and then thinking about Earth as unique in the solar system and how Earth is a place full of life. And looking at different aspects of that life, like plants, and the relationship between plants and animals, and also between animals and things like predator and prey. Thinking about life cycles, not just food chains, and thinking about energy and energy transfer as well as matter, and thinking about things like actions and reactions, and how energy transfers not only through living organisms and food chains and food webs, but also through inanimate objects and physical systems. and the different forms of energy, and also in an engineering context, how we can manipulate uh, forces and energy to solve problems. So basically, again, in that nature of science and engineering, using our scientific knowledge to actually solve problems that we identify. So you can see if we mess with this ordering, we lose those connections. And the thing is that we can intentionally develop, we can give students the opportunity to practice the science and engineering practices, to actually develop and use content, and to encounter phenomena that connects from one unit to the next all year long, so that Unit 1 has relevance to Unit 5 and Unit 6 and so on. Okay, and that's also important to avoid systemic gaps in curriculum. Every now and then we have people who will reach out and say, "Oh, you have IC standards from grade level, but also the grade level before and the grade level after." Well, you need to have not only standards that are considered by some to be grade level specific, but those are there for mastery. They need to be mastered by the end of that grade level. That's what makes them grade specific. But it doesn't mean that it's a once and done, that it only occurs in that year. They need to be introduced, mastered, and reinforced. Why? Because students come and go. Okay, and it's equity and access is important here for students. The other thing is that students develop at different rates and different times, and so students don't always get something the first time. They don't always make all the connections. So from one grade level to the next, there's this intentional nurturing process, and even within the year. Okay. The other thing that's important to realize is that performance expectations and the elements of those foundation boxes are things that are not taught in isolation. It's not a checking off of we covered, quote, covered the standard. You don't cover anything. What you do is you actually encounter it, you develop it, you use it, and you do that over and over again, and it becomes more nuanced and more connected by teaching performance expectations in combinations with others. Okay, so just people can be incredibly literal, and I just want to, if you fall into that trap, it can leave your students in a real bind, and it can leave teachers and districts in a real bind, because these are not things that are once and done and happen in isolation. So you can see, again, within a year, we're teaching across all the strands, and you can see things like energy and matter, scaffolding upward, developing and using what students know as we go within the year and from one year to the next. From a teacher's perspective, and I'll end on this, it's important to understand the progression of lessons. So this is just a screenshot off the front page of one of our grade 5 lessons, and have broad unit goals. But it's also important to understand how those grade-specific standards are unpacked and connected within different lessons in the unit, and by dimension, and also the supporting standards. So here I'm showing grade-specific for grade 5, but there are other pages that I'm not showing you that show the supporting standards for the prior grade level and the next grade level. So again, we're avoiding the systemic gaps. And here you also see the related practices by lesson too, what students are expected to engage in from those SEPs. Lastly, thinking about what's unique, because again, we're talking across K-12 and very specifically early elementary and middle school for most of our audience today. So there are some unique challenges to what I've been talking about and describing in terms of using anchor phenomena and investigative phenomena as the mode of instruction by playing that role of next generation inquiry educator, having a next generation inquiry environment, and doing so effectively at these sort of different developmental levels, different grade levels. At the early elementary level, so I'm going to consider that kindergarten to second grade, one of the key challenges is having strategies to overcome reading. So, I mean, it's most early elementary educators are used to circle discussions, read alouds, I wonder circles, and things like that. Also chunking time appropriately. Because students are so engaged, you tend to get more attention than less in these phenomena, in these discussions and planning investigations and so on. But you don't get the type of attention that you're going to get at 4th grade and 8th grade. Other piece has to do with fine motor issues. So students at this level are also dealing with fine motor skills, developing those. So the types of prototyping and experimentation that students can do from a materials perspective is much more limited. And again, the value for student learning is in engaging in higher order thinking and developing and using a context, not in cutting little boxes and in drawing little circles and things like that. So a lot of care and thought needs to be given to that. At the elementary level, we've overcome a lot of these things. So elementary, I'm talking about grades 3 to 5. So the strategies here that are necessary are to push students to become even more independent actors in the classroom, to give them even, to make sure that they are fully engaging their agency, is what I mean by this, and pushing them to be divergent thinkers. Increasing the expectations that you have for precise language. The word stuff is not enough. 5 is not enough. It's 5 what? I think I know what you mean, but I'm not sure because you haven't told me. So let's think through this together. Tell me what you mean. And you need to go back and explain that. You need to go back and tell me that. And so those are elements that we're overcoming at that 3 to 5 level. And another piece is making sure that we're getting full release of responsibility within 10 weeks of the school year. That's really key because if you don't have full release of responsibility, students do not get independent practice of the practices, and they don't get opportunities to make mistakes. And that's key. If a student can't make a mistake, then they don't really have an opportunity to learn. Because learning in this context that we're talking about, this next generation, performance expectations, means investigating things that we don't already know. Now, as adults we know it, but students don't know. And so students need to travel down a path and discover mistakes, discover assumptions that are not correct, and then react to that. That's very important. So if you don't get to full release responsibility within 10 weeks, you don't get a 10-week refinement period and a 10-week sort of super refinement kind of period where you're really able to push that student's level. And this challenge actually tends to be more with teachers and skills around releasing responsibility and people who are very stuck in a traditional model than it is students, because students tend to be all in and adults tend to be ease in. And these are kind of at odds with each other. At a middle school level, and you even see this kind of at that upper elementary level, it becomes very important to overcome separating the person from the idea. Okay, that somebody's idea may be true or false, may be supported or not supported, but that is separate and not reflective of the individual, who they are, what they are, and their value. Being honest with ourselves becomes a big issue. And both of these things are tied to that social emotional risk-taking. And so, again, to have that authentic environment driven by a broad phenomena at first and then dug into with that student-centered investigation, these become challenges at the middle school level. All things that can be overcome, all things that people who are teaching at these levels probably would shake their heads and say, yeah, I could see that. But maybe things that we kind of easy to forget because of the complexity of a lot of this stuff. Finally, what I want to do is just talk briefly about next generation state level assessment. So this is an example from DC, DC assessments. DC has an item agreement with Illinois, So if you're in Illinois, you'll see things like this, and others are coming into place over the next 12 to 36 months. A whole slew of states are going to start coming online with these types of assessments, because now that either there has been an adaptation in places like Massachusetts or an adoption in places like Arkansas, we have to assess the new standards and not the prior standards at a state level. So the key thing I want to point out here is that the assessment itself engages students in a scenario, and that scenario has anchor phenomena. And that anchor phenomena is, in this particular case, and what is most often, is something that's being investigated by two fictional or a fictional student. And the student being tested is asked to create an opinion about that and support it with evaluation and analysis of the fictional student's results. Okay, and that's what you see here. Trevor and Kayla, they did this thing in their class with hydroponics. They created this apparatus. They got these particular results. And the student being tested is asked whose claim is correct, Trevor or Kayla, because their claims are opposing, and explain why that claim is correct, and use evidence to support your choice. Okay, so this is that claim evidence reasoning model of writing and scientific argumentation, but it requires students to use their own knowledge, to be able to develop and use what's in front of them here, and to be able to navigate a framework that is really a framework, a process for science here. So this is one of the blind spots, unfortunately, in the new standards, is that it does not give specific process for science or for engineering. And I think either it was something that was overlooked in the process, but more likely, my opinion is that it was something that people felt was a bridge too far, because it's going to be a lot. It is a lot for folks to transition from traditional to next generation model of instruction. The idea of going from practices to processes, it's a lot for people. But in the case of KnowAtom, what we've done is there's really no other way to do it without process. So we involve scientific process, engineering design process, as an actual logical framework to move from the question or problem to an evidence-based conclusion. So it comes in really handy in these kind of assessments. Here's another one where you can see students are given a bunch of different organisms. Again, relates to Trevor and Kayla, even though it's a different item. And students are asked to construct a food web and actually to explain how their model shows the shortest way for energy to get from plants to the fox, and so on. Further over here, students are given a model which they didn't develop, but they have to be able to use the model to answer a specific question. So they have to analyze and evaluate it. But then they have to be able to describe the relationship between the organisms in the pond and the exchange of matter back into the environment. So they have to create their own connection. They have to create their own model, which is going to say, well, if an organism like the bass dies, the bacteria is going to act as a decomposer and actually return that matter back to the environment so it can be uptaken or reuptaken by the algae and so on and so forth. Okay. So again, phenomena. Okay, we see it here, and it kind of happens at different levels. This is much closer to investigative phenomena than it is anchor phenomena, but nonetheless, they're kind of interconnected. And you can see how students learning in this mode that we've been talking about really would prepare them for those kind of tests. If you're from a park, state, or district, you've seen that in ELA, right? You have a scenario. Students need to use support for their ideas and so on and so forth. In our curriculum, one of the ways that we approach this from an assessment standpoint is that we actually give scenarios which students have not encountered. This is after they have completed that unit, okay, those lessons, which require them to create, evaluate, and analyze by developing and using what they've learned in a very similar fashion to answer questions that relate. Okay, and that along the way we interject new information and ask students again to consider that information, work with it, develop it and use it to reflect on the student's assumptions or so on in that context. Okay, and what this shows us, it shows us basically each of these questions is showing us a different element of those foundation boxes, and give us a more complete picture of a student's ability to perform the expectation of the standards. And so this is just a couple of screenshots. With that said, I am going to have to leave here in literally a minute or two. I wanted to just give you some resources. If you have questions, feel free to reach back to me by email, because again, I'm not going to be able to get to all the questions here. If you would like to talk to someone on the phone, or you have questions, ame you've been working with Karen or so on, feel free to reach out to Karen. Her telephone number is here, and her email, KPEAKE at KnowAtom.com. And if you'd like to take a look at one of our units that is designed for next generation science standards, you can check those out at KnowAtom.com/curriculum. Our NGSS units are for NGSS adoptive states as well as California. We are aligned directly to all those. And for the adoptive states, we have versions. It depends on which state you're from, but we have versions that meet the adaptive states as well. Like Massachusetts, we have a Massachusetts specific version, and so on. And I just say that because these are nuanced, it's obviously complex, and so seeing is helpful. And then, of course, so those are free to download. You can take a look at those. It's only the first sort of unit, month's worth of teacher binder and the students' sort of reading material. Obviously, we have these for purchase with all of the hands-on materials to do the experimenting and prototyping. That's how we pay our bills and keep the lights on. And if you hopefully got some benefit out of this and you are interested to stay connected, you can join our blog for free, KnowAtom.com/blog. Follow us on Facebook or Twitter, where we announce a lot of these kind of events. So it's been a pleasure to have you with us. I'm going to just give a quick look down the questions and see if I can answer one or two before I head out. Okay. Okay, some folks have asked questions around things like bundling concepts, and I think I've already addressed this, but that is, that's what I'm talking about. You're grouping concepts, you're grouping standards, and so on and so forth. And in terms of the types of models that we use, 5E, 4C, understanding by design, all of this is what we are doing here. We have a very complex, it's actually like 20-stage process for developing units and aligning them. So that's proprietary. we don't actually distribute that, but it's sort of an amalgamation of a number of these pieces, because unfortunately any one model in and of itself is too basic to really get a cohesive system together across all grade levels the way that it needs to be, and particularly in a way that can be generalized and used by multiple folks. For one person to do it for themselves, it's a huge time investment for one person, but obviously it's like a recipe. Curriculum in some respects is often like recipes, where if you know what you mean by something, that may be sufficient. But if somebody else doesn't know, how can they be supporting you effectively, either as a peer teacher at the same grade level or at a